Thank you very much. So it's a great pleasure to have the chance to speak at this very interesting meeting in honor of Mike's 60th birthday. I was trying to remember when and where we first met, and I couldn't remember whether it was probably in the States, but I think one of the earliest distinct memories is of some of the memorable seminars I heard you give in Paris back then. But since then, we've been friends and colleagues for a long time and spent a long time discussing all sorts of things, often over very good dinners. One particularly memorable dinner was one we went to with Paul Townsend, which instead of having a wine paired with each course, it had a cognac paired with each course, and I think that dinner was particularly inspirational. But often my discussions with Mike have been very inspirational. Often, his ideas have been things which perhaps, sometimes it took me some time afterwards before I fully understood the importance of some of the things he was saying. But it was always been a pleasure to share these discussions with you. I spent quite a bit of time visiting him in Rutgers and later Stony Brook, and then and together we joint organize, as well as his organization of things in France. He also was a joint organizer of a very successful program at the Newton Institute on M theory. What I want to talk about today is based on something which Mike's been interested. The starting point is something which Mike's been interested in for a long time and played an influential role in. And one of the things we spent a lot of time talking about back during some of my early visits in Rutgers. And this is the relationship between five-dimensional supersymmetric Yangmills and a six-dimensional theory with 2,0 theory, supersymmetry, which is believed to arise from this as a strong coupling limit. It's believed that in strong coupling, the five-dimensional super Yangmills, suitably embedded in an ultraviolet complete theory, at strong coupling gains an extra dimension in a way very reminiscent and in fact deeply related to the way 10-dimensional string theory gains an extra dimension to go up to 11 dimensions. And this extra dimension opens up, and so we can think about the 2-0 theory compactified on a circle where the radius of the circle gives rise to the dimensionful Yangmills coupling constant in 5 dimensions. And so as the coupling constant goes to infinity, the radius decompactifies and you get a 6-dimensional theory. There are indirect arguments that there should be such a such a 6-dimensional theory exists, but it's been proved very elusive. There's a natural super multiplet which exists in 6 dimensions, which instead of having a vector field as in the 5-dimensional Yangmills, has a 2-form whose 3-form field strength is self-dual, but it's not clear whether it's not even clear whether these provide the right fundamental degrees of freedom for the 2-0 theory, or whether there's something more exotic going on. And what we do know is that it's a non-Lagrangian theory, in that there's no conventional action which is local and covariant and has all the usual properties, at least no conventional action based on this super multiplet. So it's proved rather elusive, and although it's been known about for quite some time, it's still tantalizing that despite the amount we've learnt about it, that we still have very little direct understanding about what this theory is. An important part of this is that if we look at the W bosons which exist in 5 dimensions in the Yangmills theory, these lift in the 6-dimensional theory to strings, And if you, as you take the Higgs vacuum expectation value to 0, so that the W bosons become massless, then these corresponding strings have a tension which is approaching 0. So it's long been suspected that some tensionless strings, in some sense, might play a role in understanding what this 2-0 theory is. Another key and very important feature of this 2-0 theory is that it's superconformal. It's got, when the symmetry is unbroken, then it's got a large superconformal invariance, and in particular, there's no dimensionful coupling constants in 6 dimensions. So it's a very interesting and elusive theory. And what I was, the idea I was looking at back during one of my visits to Rutgers is to look for a gravitational analog of this. So it turns out that there's a 4,0 supermultiplet with twice as many supersymmetries as the 2-0 one. It has no graviton on it, but just as the 2-0 multiplet has no photon, but nonetheless, dimensional reduction on a circle gives a 5-dimensional supergravity multiplet. And at least in the linearized theory, you see that if you compactify on a circle of radius r, this gives rise to the gravitational coupling constant in 5 dimensions, which are represented by the 5-dimensional Planck length. So this led to the rather interesting proposal that the strong coupling limit of just as the strong coupling limit of the 5-dimensional Yangmills theory could give rise to a 2-dimensional theory in 2-0 theory in 6 dimensions, that a similar thing could be going on here, that a theory that the strong coupling limit in 6 dimensions could be a theory with 4,0 supersymmetry. And so it would be another story where extra dimensions would open up at strong coupling, and the naught branes in 5 dimensions would lift to 6-dimensional strings. And so this was the idea I was looking at around the time in these papers from now long ago. And it's these ideas which I want to revisit in this talk today. So this remarkable supermultiplet is in some sense a square of the 2-0 supermultiplet, and I'll describe that in a moment. And instead of the graviton with 2 indices, it's got what I'm referring to as an exotic tensor, which has got 4 indices. So maybe this is an overuse of the word exotic, and I see that Natty Seiberg later on in this session is giving a talk on exotic field theories, and I'll leave it to the audience to decide which is the more exotic. But nonetheless, this multiplet reduces to the 5-dimensional supergravity multiplet in the way, and I'll say a bit more about that in a moment. And so there's a possibility that this is giving rise to an exotic theory of gravity. And what's remarkable about this multiplet is that it's superconformal. So this would be a theory which gives rise to 5-dimensional supergravity, but nonetheless is at the fundamental scale superconformal. So this would be a way of getting a theory of gravity which was conformal. This could be a way of getting a super theory of gravity which is conformal, and yet avoids the higher derivatives which seem to be unavoidable in more conventional approaches to conformal gravity. But the elephant in the room in this discussion is the question of the interactions. So just as the 2-0 theory, the 2-0 multiplet, there are no conventional actions or interactions one can write down. There are no-go theorems. The same is true for this 4-0 multiplet. There's no conventional local covariant action or even field equations one can write down. But we know for the 2-0 theory that there is a non-Lagrangian, it's a non-Lagrangian theory. It exists nonetheless. And we've learnt in recent years that there's a large menagerie of non-Lagrangian theories, and so the question arises as whether there could be an interacting non-Lagrangian theory for this supermultiplet. So if there is, this would be giving some exotic theory of gravity, and we already have a very good theory of gravity, so we might ask why one might want an exotic theory of gravity. And it comes from asking about what happens at and beyond the Planck scale. It's long been suspected that there could be a radically different theory beyond the Planck scale. Maybe one idea is that there could be a new highly symmetric phase. Another could be that the picture of a conventional space-time, a smooth space-time equipped with fields would break down. Maybe there's some different structure, perhaps a matrix structure or some other discrete structure from which the continuum arises in some limit. Another idea is that there could be something like a tensionless string limit, and an old idea which was explored by Gross and Mende was when they looked at high energy scattering in string theory. They found evidence that of a phase at high energies, at ultra high energies, in which there was perhaps a very large, highly symmetric phase. It's another attractive idea which has long been held as attractive is that thought to be attractive is that the fundamental theory should be conformal, and that the dimension scales would arise from some kind of a spontaneous breaking. So these ideas, these kinds of ideas have been around for quite a long time. But quite recently, there's been some very interesting progress in at least some of these ideas. And so, for the first time, we're actually seeing explicit realizations of some of these ideas in a concrete model. And I want to use this as an excuse to digress slightly and say something about some recent work I've been involved in on tensionless strings. And one place in which one can make some concrete progress in some of these ideas is in anti-de Sitter space, where there's a dimensionless coupling given by the ratio of the string tension to the cosmological constant. And in this context, this is a controllable dimensionless coupling, and we can ask about what happens when that's large or small. And in particular, if we take a limit in which this goes, and this becomes small, in which the tension becomes much less than the anti-de Sitter scale, then the strings are becoming, have tensions going towards zero. And it's long been argued that there should be a limit in which there's infinite number of massless higher spin gauge fields arising, that the infinite towers of massive fields one gets in string theory collapse down to massless fields with a large infinite symmetry and perhaps a Vasiliev type gauge algebra. And in particular, one particular context where one can make some very explicit progress in this is if you look at three-dimensional anti-de Sitter space with a flux given by the fundamental 2 form, field strength in the fundamental 2 form, then this has an explicit description as a Westerminer-Witten model with gauge group SL2R of level K. And this is something which has been explored in great detail by Maldacena and Aguri. And so for generic levels. And so it's within this context, we can look explicitly at the question about whether these ideas are realized and look at them, get a precise description within string theory. So if one looks at the affine SL2 algebra, it turns out to be critical in a certain sense at the level it approaches 2. And one of the features of this criticality is that there's an infinite number of null states appearing in the representations. And this led to the suggestion some time ago that at this limit, in which critical limit, there should be indeed such an infinite symmetry arising. However, a few years ago with Gabadil and Gopakuma, we looked explicitly at this and looked at the explicit worldsheet formulation of the string theory in terms of the Vesemina-Witten model, and in particular, we wanted to understand what happens as we approached k equals 2. And very surprisingly, we found that something rather unexpected and different from what we were expecting was happening, and that there was an infinite symmetry arising, but it arose at k equals 3 and not k equals 2. And the meaning of that was that k equals 2 is where we would expect the conventional degrees of freedom we'd expect to do with rising from small strings moving in anti-de Sitter space to become critical. But in fact, before you get there, there are long strings in the spectrum of the model which live near the boundary of the anti-de Sitter space. And it's these unfamiliar long strings which are becoming tensionless and driving this story. And because the size of the anti-de Sitter space, well, the anti-de Sitter radius is of the order of the Planck scale in this case, things being at the boundary are not so, in a sense, not so far away. And it's perhaps in this ultra-Planckian limit, the long strings playing a key role is perhaps not quite so surprising, but it was rather interesting that this happened. For the superstring, with Neveu-Schwarz flux, there's a similar thing which happens, but with the familiar shift of 2, giving a critical value at 1. With Girobet, Kleben, Parati, and Rabinovici, I argued that this is an indication of a phase transition from a phase dominated by black holes, a familiar gravity phase, to a phase dominated by these long strings. And since then, there's been much subsequent work, including extensions to ADS5, particularly by Gabadil, Gopakuma, and Eberhardt, but many others also involved in this. So the point of this was to show that we're beginning to get some of these kinds of exotic phases some of these exotic phases are ones where we are beginning to be able to get some control, and so maybe there's some hope that we might be able to make some progress in the kinds of exotic phases I was referring to in the introduction. So let's return to the story of the 4-0 supermultiplet. In 6 dimensions, the little group is SO4, or SU2 cross SU2, and the physical states are in these representations here. USP8 or SP4 is the R-symmetry group. And this multiplet, the physical states were written down long ago by Strathty, but I think no one had done anything with them for quite a while. I rediscovered this and worked out the covariant field content. And so there are 27 two-forms with self-dual field strength, which sit up here. And there's this exotic tensor here, which sits here. And instead of a gravitino, we get a spinor-valued two-form here with self-dual field strength. So the bosonic fields are 42 scalars, the 27 two-forms, and this gauge field. And the symmetry properties of this are those of the Riemann tensor, so it's represented by this Young tableau. And there's a corresponding field strength where we take 2 derivatives and then anti-symmetrize according to this Young tableau. And this field is self-dual on the first 3 indices corresponding to this column, these 3 indices, and self-dual on these 3 indices corresponding to the second column. And this theory has a very large symmetry. It's got 32 normal supersymmetries, 32 superconformal ones. And in particular, it doesn't contain a graviton, as I mentioned. So if we look at the corresponding 2-0 free theory, the 2-0 multiplet, it has this superconformal group, and its field content consists of a 2-form Fermi spin half fields and 5 scalars. And reducing to 5 dimensions, the 2-form would normally, reducing a normal 2-form would give rise to a 2-form and a vector field. But the self-duality constraint on the field strength of B then becomes a constraint that the field strength of A is the Hodge dual of the field strength of B, so that they're not independent, they're related by electromagnetic duality, and so you should only count them once, and so we can regard it as giving a 5-dimensional vector multiplet with a vector. Although it's interesting that it comes about in a rather democratic formulation with both the field and its dual arising. So in d dimensions, so just a reminder that a photon is represented by a vector field with this Young tableau, and its dual is a d-3 form whose field strength is the Hodge dual of the usual 2-form. And this gives a dual formulation of the free theory, but of course it doesn't extend to the non-abelian theory. So this work led me to think about the generalization of this to linearized gravity. And I was rather surprised to see that this didn't seem to exist in the literature beforehand. So there's a similar idea if you start off with a graviton. So I'll use this notation 2, 2 to represent, for example, a Young tableau to label the dimensions of each of the 2 columns of a Young tableau. So the metric is a 1, 1 object. The field strength is a 2, 2 object. And one can dualize this vector to a d-3 form, as I did for the for the vector field on the last slide, to get a dual graviton, which has got this Young tableau and n indices here and 1 here. Or one can dualize on both indices and get what I called a double dual graviton. And the corresponding field strengths where you have 2 more derivatives and you add 1 box to each of the 2 columns. And the key thing is that the duality exchanges the field equations and the Bianchi identities, and these are related by, one of them is given by the dual on one side, say on the first 2 indices, and the second one is given by dualizing on the first 2 indices and on the second 2 indices. And in this way one finds that gives a natural framework, at least in linearized gravity, for thinking about magnetic sources, which are magnetic analogues of the mass, or the energy momentum, which are thought of as electric sources. And there's a very nice story one can talk about there, at least in the context of the linearized theory. So now this gives us the information we need the ammunition we need to look at the reduction of the theory that's from 6 to 5. The 2-form fields give 27 vectors in the way we described. The scalars give scalars. And if we look at the 4-index object, we construct 3 types of tensor, depending on whether 2, 1, or 0 of the indices are in the compact 5 direction. And in this way we get 3 objects, and in 5 dimensions, these are the right structure for this to be the graviton, the dual graviton, and the double dual graviton. And here one finds that the self-duality constraints of the field in 6 dimensions imply that all of these fields are dual to each other, so there's only one independent field, and one gets And so we could formulate it just in terms of the gravitons, say. And the diffeomorphisms in 5 dimensions arise from the gauge transformations of this exotic field C, which have indices with have 3 indices in this Young tableau. And if there's time, I'll say a bit more about that at the end. So,
Chris, so the A index was the fundamental of some kind of spin asymmetry?
Yeah, so the little a indices, if we go back, yeah, here, these A's run from 1 to 8 and they're SP4 indices, yeah, or USP8 as it used to be called. And so here we have 8 of these, 27 of these, 42 of these, and I can't remember the number here.
It's really in flat space, right? Everything.
Here I'm looking at the linearized theory in a Minkowski space background, and the question about going beyond that is what I'm going to come to in a moment.
Can you say if it works or not? Or maybe you have no answer.
We don't know yet, but so part of the purpose of this talk is to give a status update on what we know about this, and I'll come to that in a moment.
So SP4 is not gauge; it's a global symmetry.
It's a global asymmetry, so it's just like when you reduce down to 5-dimensional supergravity, there's an SP4 asymmetry and an E6 global duality symmetry. And the SP4 in 6 dimensions would reduce to the SP4 in...
And supersymmetry is...
SP4 is the same thing as spin 5, right?
Sorry?
SP4 is the same thing as spin 5?
That's correct, yes. Yeah.
Can you tell us is there a simple coset manifold with 42 scalar span, and do you know its form?
So the natural coset space which this wants to talk to is E6 over SP4. So that's what would give the 42 scalars. But in a free theory, so when you reduce down to 5 dimensions, we know that the 42 scalars in 6 dimensions give rise to 42 scalars in that coset. But because of we don't know what the self-interactions are in 6, we can't quite say that it's, we can't be that explicit in 6.
Sorry. The spinor indices, do they figure on your...
They're suppressed. So there's also, here there's a spinor index, there's a 6-dimensional spinor index here.
Which is hidden. And
here, which is hidden and chiral. So in light cone gauge you get,
yes.
This is a 4,1 of the SO4, and this is a doublet of the SO4. Okay. So here we're getting chiral spinors only of 1 chirality in the spin half. Any other questions before I go on? Okay. Where do we get to? Yep. And at the level of the representation theory, we can think of the free supergravity as being constructed from the tensor product of the physical states of the Yangmills multiplet. And a similar story happens here in that the free 4-0 theory can be thought of as being the multiplet as being the tensor product of 2 2-0 multiplets. But the key question is that of whether there are interacting theories. So for both the free 2-0 and 4-0 theories, there are no classical covariant local interacting extensions, and there are explicit no-go theorems for that. But we know that there is an interacting 2-0 quantum superconformal field theory, which reduces to 5-dimensional super Yang-Mills. This arises as the world volume theory of the M5 brane, and we know that it's a non-Lagrangian theory. And so this brings us to the question about whether there could be an interacting 4-0 superconformal field theory, reducing to 5 dimensional supergravity. So, I mean, there are two possibilities at this stage. There's the boring one, which is that there's this beautiful multiplet which could do all these wonderful things for us, but it's the only multiplet with 32 supercharges or less, which doesn't seem to play any role in the M-theory game. Or there's a possibility that it could be the key to constructing some exotic theory which could give a conformal theory of gravity. And of course, it's very important to know which way the world goes and whether there really is an interacting theory, and whether it, first of all, whether it exists, and secondly, whether it plays the role I've suggested in the M-theory story. So let's remind ourselves about the story of the five-dimensional super Yangmills. If one looks at the five-dimensional superalgebra, so here alpha are the spinor indices and A are the SP2 or USP4 R-symmetry indices, then the superalgebra takes this form. So there's a standard P dot gamma term with a charge conjugation matrix in there. And there are some naught form central charges which are carried by the W bosons, and the number of these is precisely the right numbers to be the charges carried by BPSW bosons. And then there's an extra charge K, which is a singlet under the R-symmetry. And this is carried by the following objects. If we think about a Yangmills instanton in R4, a solution of the self-dual Yangmills equations, if you take the product of that solution with that space with time, you construct a soliton in 4+1 dimensions, where the point-like instanton, where there's the localized instanton, now becomes is lifted to the world line of a soliton, and these carry the charge K. And in particular, this K is proportional to the instanton number, the Yangmills instanton number. And the mass of these things is given by this integer, some 4 pi's, which I'm suppressing, and 1 over the Yangmills coupling constant squared. This has got the dimensions of length in 5 dimensions. And so here we see that there's these become light at strong coupling, and we can think of this as, and this has been argued to be interpreted as a Kaluza-Klein tower for a 6th dimension, that this, the charge n corresponds to a Kaluza-Klein mode with momentum n over the radius. And so in particular at strong coupling, this would decompactify to the 2-0 theory in 6 dimensions. And in 6 dimensions, this K is becoming the 6th component of momentum. So, the 5-dimensional Yangmills is non-renormalizable. Mike and collaborators explicitly, heroically calculated a 6-loop divergence in this theory. But nonetheless, we can embed this within string theory, for example, as a volume theory of a D4 brane, and within this ultraviolet complete theory, we can explore these questions. The strong coupling limit is defined within string theory, in which the D4 branes lift to M5 branes, and in taking this limit, because the Yangmills coupling is dimensionful, it's better not to think of it as taking this to infinity, but rather to one looking at high energies, in particular to energies much higher than the Yangmills scale. And so it's a physically meaningful question is we're looking at ultra high energies much higher than the Yangmills scale that we're seeing this structure emerging. So now we can look at the same game in supergravity. We get exactly the same superalgebra. So I'm suppressing one form and higher form charges in this slides. The only difference now is these index A runs from 1 to 8 instead of 1 to 4. Again, there are some naught form charges. There are 27 of these, and these correspond to the 27 kinds of naught brane charge one gets in 5-dimensional supergravity. And then there's an extra charge which is a singlet under the R symmetry, and in fact is a singlet under U duality in 5 dimensions. And if there are states carrying this charge if there are BPS states in this carrying this charge in 5 dimensions, and they have this spectrum, then then the same argument as we saw before might come into play, and we'd expect these to become light at strong coupling, or rather we're looking at a high energy limit where the energy is much higher than the Planck scale. So this would be something which is happening at trans-Planckian energies. And this would be a decompactification limit with the states carrying this charge K becoming a Kaluza-Klein tower. And if this happens, the super multiplet structure says that the theory you get in 6 dimensions, the result of this, must be one with 4,0 supersymmetry. So this is the idea, and then the key question depends on what the spectrum is of states carrying this charge. So these are not related by duality to any of the familiar brane charges, it's possible that there's a possible charge which could occur in the superalgebra, but in M theory, there are no states carrying this charge. So this is what I want to say a bit more about. So if we look at, so in each of these cases, we can look for states carrying the charge K of the form which are 4-dimensional instantons times time. So instantons in 4-dimensional Euclidean space times time. So we've seen that in the 2-0 theory, that these correspond to Yangmills instantons times time. If we look at the free 2-0 theory, compactified on a circle, this momentum can be associated with singular 0-size instantons in the Maxwell theory. There are no finite size ones in the Abelian theory. If this is seen as embedded as some symmetry breaking from a Yang-Mills theory, then restoring the symmetry gives the instantons finite size. But even in the interacting theory, if one goes to the Coulomb phase by breaking all the symmetry down to the Abelian group, then again the instantons become singular and 0 size. So at least in this context, we know that there are states carrying this charge, and they're represented by 0-size singular instantons. And so there's a question about whether the similar thing could happen in the gravitational theory. And in the free theory, then the same arguments here as leads us to associate the free theory compactified on a circle gives states carrying momentum, and these can be formally identified with 0-size singular gravitational instantons of the linearized theory. The linearized theory doesn't have any finite size instantons, and the charge K is associated with the instanton number. And so in the interacting theory, there's a question about whether what happens if we turn on interactions. Could we look for states carrying this charge from gravitational instantons?
Either do you define the spin connection somehow to solve this, to get the equation defining the gravitational instantons?
Yeah, so here it's, because they're singular and 0, so if, let me come back to that when we look at the if we look in the context of the interacting 5-dimensional supergravity, then we'd be looking at the case where the curvature tensor would be self-dual, and hence you could choose a self-dual connection.
Yeah, and then the spin connection is under the carpet, or it's explicit?
The spin connection is, I mean, you can choose a gauge in which it's explicit and takes values in that. I mean, it's not gauge invariant, so there isn't a general argument, but I'll say a bit more about this once I've introduced a bit more ideas. So this should be really thought about in the context of M theory, where we think about M theory compactified on a 6 torus, which gives a theory whose low energy limit is the 5-dimensional supergravity we've been talking about. And then in this context, the naught branes in 5 dimensions and the strings would lift to strings in 6 dimensions. And possibly these would be strings which would whose tension would might become, and these might be associated with strings which become tensionless in the conformal limit. In the context of M theory, we're looking. So if there's a this 5-dimensional theory has a strong coupling limit, which is the 4-0 theory, then compactifying this theory on the circle would give Kaluza-Klein modes which carry this charge K, and this would be the momentum on this circle. And so the key question is whether M theory compactified to 5 dimensions has such BPS states carrying K. And this is a question which we could have asked independent of the whole story I've been talking about here. It's a question about the BPS spectrum in M theory. And we know a lot about the BPS spectrum, but there's an interesting question about whether there's some extra states which might have been missed. In particular, these ones are singlets under the E6Z U duality in 5 dimensions. And so these would not be dual to any other states. And if there are no such states, then this would be showing that these ideas about a strong coupling limit were not correct, and there wasn't such a limit. But if there were some, then this would be a necessary condition for the strong coupling limit to be of the kind I said. So this gives a precise question which could be asked within M theory about the BPS spectrum, which would be a smoking gun for the kind of limits for the existence of a 4-0 theory. So I've mentioned the K charge. An explicit expression can be calculated from the supersymmetry algebra. If we consider the 5-dimensional theory compactified to 4 dimensions on an extra circle, there are states which carry this charge K, and these are precisely the K Kaluza-Klein monopoles. So with different boundary conditions, we know that there are states, non-trivial states, carrying this K. And in 5 dimensions with the right asymptotics, in other words, asymptotically going to flat space, there are multi-center solutions which have the right asymptotics, where there's a number of centers, each of which is associated with something carrying K charge. So we know that there are some aspects of K charge which definitely do exist in this theory. So if we're looking at gravitational instantons, we know that in 4 dimensions, if we look for non-singular solutions, there's, to a large extent, they've been classified. There are ALE solutions, which are asymptotically locally Euclidean, tending to asymptotically to R4, modded out by a discrete group. In the usual case, familiar case ZQ, but there are other discrete groups are also possible. And so we can certainly have instantons which are non-singular and asymptotic to a quotient of flat space. But instead we could also, there's also the possibility of having ones which are asymptotic to flat space but are singular. We already saw that in the free theory, where we saw there was singular zero-size instantons arising. And so the question arises is whether there could be BPS states carrying this charge K corresponding to singular supergravity solutions. And as a parenthetical remark, if the metric is not fundamental, if at very short distances the metric's replaced by an exotic tensor, then having at large distances a singular metric which has singularities at short distances. So having a metric which becomes singular at short distances might not be so bad because there might be a core where the metric is replaced by this other field. So for the 2-0 and 4-0 conformal field theories, there's no local interacting field theory, no local covariant interacting field theory. The 5-dimensional naught branes and magnetic strings lift to self-dual strings in 6 dimensions, which may become tensionless in certain limits. As a very large superconformal symmetry, the 4-0 has more supersymmetries than any other theory in the game. And both the key gauge fields lift to self-dual tensor gauge fields. And in the 6-dimensional theory, there would be no fundamental scale. The dimensionful scales would all rise from compactification. So there's another way in which we could try and get a handle on what the interactions might be. And that comes from the so-called double copy construction. In 4, 5, and 6 dimensions, supergravity amplitudes can be constructed in a certain sense from squaring super Yang-Mills amplitudes. More precisely, if one looks at the integrand and the expressions from the formula for the amplitudes, the integrands in the supergravity theory can be of the amplitudes can be constructed from the squares of the integrands of the Yang-Mills amplitudes, and there's a precise, at least at the tree level, and with some progress on understanding what happens beyond tree level. And so there's a one-to-one correspondence between the amplitudes in these cases. And so this leads to the idea that one might try and take amplitudes for the 2-0 theory and square these to construct the 4-0 amplitudes. But one of the problems is that we don't have explicit expressions for the 2-0 theory amplitudes, and being a conformal field theory, it's not even immediately clear that's the right thing one might look at. So one could also think about taking correlation functions and seeing if those could be squared to give correlation functions here. There has been some work by two groups which construct formal expressions for 2-0 amplitudes, albeit with some issues, and then the resulting 4-0 construct resulting 4-0 amplitudes. There's a number of problems. One of the 2-0 amplitudes constructed so far are they're 2-0 supersymmetric and have a lot of nice features, but they only exist for even numbers of external particles, and they also have strange poles where the residues appear to correspond to some kind of non-locality. So the interpretation of these expressions is rather problematic, but it's very interesting that these expressions exist, and be interesting to understand what question these nice expressions might be the answer to, if not this one. But I think understanding the 2-0 theory better and understanding what the particular amplitudes or correlation functions are there explicitly would then enable one to construct amplitudes and interactions in the 4-0 theory. And a key thing is that these 2-0 amplitudes should reduce down to Yang-Mills amplitudes in 5 dimensions. It was shown that these ones constructed here by these authors had that property, and that the 4-0 amplitudes also indeed reduced to 5D supergravity amplitudes. How am I doing for time?
5 minutes.
Okay, so running out of time, so maybe I'll just skip this bit and go to the conclusions. So we've seen that so in 6 dimensions there's an exotic free 4,0 theory. It's a conformal theory of an exotic graviton, and it reduces to linearized 5-dimensional supergravity in 5 dimensions. And so it's remarkably is a theory of a gravity without a graviton. And remarkably, it's conformal. It gives rise to a two-derivative theory in less than 6 dimensions for a conventional graviton. One thing I haven't had time to talk about is if you compactify on a 2 torus instead of a circle, then the SL2Z acting naturally on the 2 torus gives a gravitational analog of S duality, which is, gives some rather interesting features. This is, again, something which works very nicely in the linearized gravity. And a key feature is that it's not the usual space-time, so there's no metric or diffeomorphisms arising in 6 dimensions. And one of the problems which I haven't had time to talk about is that I'm formulating everything in a background Minkowski space. And so when you reduce down to 5 dimensions, you have a graviton moving in Minkowski space, and you have, and you know how to assemble those into the total graviton. But here, the background, which is described by a metric, and the fluctuations, which is described by the exotic tensor, are hard to fit together. And so to go beyond this story, one would need to try and find a better arena for discussing this structure beyond the free level. So the key question is whether an interacting theory exists. As I said, it's possible that this is one theory which just exists as a free theory, and that none of the fantasies I've talked about actually is a reality. It would be a disappointing but perfectly logically possible outcome. But if there is an interacting theory, I mean, its consequences would be far-reaching, and so surely it's very interesting to understand that. And it's possible that this theory exists, but it's got nothing to do with M theory. But I'm particularly interested in the possibility it arises as a kind of Transplanckian limit of M theory. And I focused on a key issue, which is what the spectrum of BPS states in 5 dimensions is carrying this charge K. Because we want them to represent gravitons in 5 dimensions, Kaluza-Klein modes in 5 dimensions, we would want them to have the usual boundary conditions for a particle. In particular, we wouldn't want them to be ALE boundary conditions, but asymptotically Euclidean boundary conditions for the instanton. There are no non-singular asymptotically Euclidean instantons, gravitational instantons. So this forces us that if this is to work, it forces us into the situation of confronting the possibility that these BPS states would be represented by singular solutions. But this is something which we're used to in M theory, that many of the branes we've come to know and love are in fact represented by singular supergravity solutions. And an alternative argument, which is in a sense independent of this one, which is the approach from amplitudes, where one might try and approach constructing 4 zero amplitudes from the square of 2 zero ones, which of course brings us back to the question about understanding what the 2 zero theory is, and what the and what in particular what it means to construct what the amplitudes or correlation functions would be for that. So one of the reasons why I dropped this whole program for a while was that I realized that a lot of what I was doing with the 4 zero theory was very closely related to things which were being done with the 2 zero, questions which arose in the 2 zero theory. And my naive idea was that the 2 zero theory was something which people would sort out very soon. So I just had to wait a few years while people found out what the 2 zero theory was and understood what that was. And then I would just square it and it would tell me what the 4 zero theory was. But it's been a while and I've grown impatient. So I was coming back to look and see whether there are other questions one could ask in the meantime. There's another a player in the game which I haven't discussed in this talk, which is one with 3,1 supersymmetry, which again is an exotic multiplet with an exotic graviton. It works slightly different. It's not a conformal theory, and so there's also a question about what role that might play. Again, this amplitudes for this 3,1 multiplet could be constructed, instead of from squaring 2,0 multiplet amplitudes, from a product of 2 2 0 amplitudes and 1 1 amplitudes. And so again, there might be a theory here which might play a role in the game. But independent of whether all these questions are, whether this 4-0 story is part of the M-theory game, there's a sharp question there's a key question I don't know why it's gone back the way back. Okay, so there's a key question, which is, what is M-theory at ultra-high energies? There are indications from, for example, Gross and Mende about some hidden structure arising in string theory at ultra-high energies. And there are other indications from tensionless string limits in anti de Sitter space. And there are various other issues, ideas which might play a role here. But there's a question about whether there could be some simplification or some interesting structure which might arise at higher energies, some highly symmetric phase of M-theory. And maybe the ideas I've talked about today might give us some handle into what that might be, or maybe the answer will be something altogether more exotic. And so with that open question, I'll like to wish Mike a happy 60th, or belated happy 60th, and stop there. Thank you.
Are there some questions?
Chris, could you quickly show us the slides you skipped, the analog that diffeomorphism?
Yeah, sure. Yeah. So for the free theory, it can be formulated as a conventional field theory in a flat background, where we have background diffeomorphisms, which is just the diffeomorphisms of the Minkowski space. In particular, it's the Poincaré group acting on the conformal transformations. But then there are gauge transformations which apply for this gauge field. It's got 4 indices. The parameters have got 1 less index, and then so you've got an object which has got a hook Young tableau and 3 indices, and you have 1 derivative, and then you have the Young symmetrization there. When you reduce down to 5 or 4 dimensions, then we combine them. Then we get the C field gives rise to a metric, and we learnt to combine the background metric with the fluctuation and get the total metric G mu nu. And then we see how the two kinds of symmetries, the background diffeomorphisms and the gauge transformations of the field, are essentially seen as 2 aspects of the same thing, related from one to the other by the shift symmetry, which shifts between the background and the fluctuation. And if you reduce down on a 2 torus, the background diffeomorphisms give the S duality of both the spin 1 and the spin 2 fields in 4 dimensions. This is unlike the S duality one was more familiar with, which acts on the spin 1 and leaves the spin 2 alone. But the problem with the interacting theory is that we don't know how to combine the backgrounds for the metric and the 4-index object. We don't expect, maybe we don't expect 6-dimensional diffeomorphisms, but these exotic symmetries which give rise to the 5-dimensional diffeomorphisms on reduction. Maybe it's an indication that we're looking at a particle theory, but some kind of tensionless string theory. So without the 6-dimensional diffeomorphisms, there's no reason to expect the SL2Z, and so there's not a derivation of the gravitational S duality in this interacting case. And there's also the question about whether without the 6-dimensional diffeomorphisms, well, with the gauge symmetries not corresponding to 6-dimensional diffeomorphisms, should the space-time be replaced by something more exotic? Or do we have a story where we have diffeomorphisms, we have a conventional manifold, but we have a gauge field with these exotic gauge transformations, whose relationship with the diffeomorphisms only comes when you reduce? And I can't help feeling that understanding the interactions must be related to understanding the nature of the relationship between space-time and the structure of this tensor field. And it's rather intriguing and very suggestive that this is suggesting a more general kind of structure. One natural idea is that that I spoke about long ago is that if you, since this is a symmetric tensor between two pairs of two forms, this could be thought of as some sort of metric on two forms, or in other words, on world volumes. So this is, or areas, as opposed to this one, which is a metric on lengths. And so maybe this ties in with the idea of some sort of, this being some sort of intrinsically stringy kind of theory rather than a particle-like theory. But nonetheless, everything's very highly constrained because the free limit should be a conventional theory, and the reduction down to 5 dimensions should again give rise to a conventional 5-dimensional gravity theory with conventional properties. Yeah. I'm not sure. Is this someone's phone call or?
That's Elias there.
He's a ghost. So I think we are a bit short of time.
Okay.
Are there a quick question?
Okay, thank you very much.